All right, let's go into a little more detail with acid and base strength. All right, so when you have an acid and you put that in water, acid, there's my base, right? You get the conjugate acid, conjugate base, right? So your conjugate base is everything that remains of the acid after it kicked off the proton, and then the conjugate acid, that's what happens when the base accepts the proton. Yay, cool. All right, let's get into more stuff here. So acid strength. So the stronger your acid is, the more that ionization equilibrium lies to the right. And in fact, for like the actual 7 strong acids, it's so far to the right that we don't even write the equilibrium arrows. It's just an arrow, just completely over to the right. Stronger acid is, the weaker its conjugate base will be. And if you have a weak acid, right, the weaker the acid, the more the equilibrium lies to the left, right, to the non-dissociated side of things, right? And the weaker your acid is, the stronger its conjugate base will be. So if I take a strong acid, so what makes a strong acid is that it dissociates 100%. So a strong acid, you put it in, boom, 100% of it, it's broken up, H plus, A minus. So this is like generic, this is fake acid, by the way. Could be any acid, but obviously this one's a strong acid. Let's say HB, here's another fake acid, right? But this one's a weak acid. And why do we know it's weak? Because it's mostly intact. There's actually only one that's broken up, right? So partial dissociation as opposed to 100% complete dissociation. So strong acids dissociate fully. Weak acids dissociate partially. All right, you're gonna have to forgive me. I'm gonna write with my mouse, and it's gonna be horrible, but hey, we'll try. I'm gonna tell you about something called Ka. All right, this is your acid dissociation constant. Let me switch. Gosh, there we go. Ink color. Sorry, I thought I had this switched. Actually, I did have it switched, but hey, wackiness. I could write KEQ for this, right? KEQ, the equilibrium constant expression. It's products over reactants. The coefficients become exponents. Sorry. Solids and liquids don't go in, so I'm kind of like doing that all in my head before I get going here. I know the water's not going in, so I'm going to get the KEQ here. I'm just going to call it K for now. Equals, it's going to be our hydronium concentration, H3O plus. Again, I'm writing with a mouse. Forgive me. Times the concentration of A minus. That's our conjugate base. Boop. And this is all over the original acid concentration, HA. Yeehaw. All right. This KEQ is so special, they give it its own name. This is Ka. All right. It's just KEQ for an acid. All right. It's the acid ionization constant. And the value, the actual numerical value of this tells me how strong the acid is, right? The more this equilibrium lies to the right, the more hydronium I have, right? The stronger the acid is going to be, right? So I can look at Ka values and right away say like, oh, if I have a bunch of weak acids, they're not all equally weak. I can say based on their Ka values, oh, this one's going to be stronger than this one or vice versa. So let's keep on rocking there. So I can look at Ka values. So other ways to describe acid strength here. So the Ka value, if Ka is large, it's a strong acid or a stronger acid. The 7 true strong acids, right? They don't even list Ka. If you go to look up Ka for one of the 7 strong acids, it'll usually say large or something goofy like that. They won't even give you a number. It's just kind of like off the charts. Ka is weak, or sorry, Ka is small for a weak acid. I was reading crooked there. Your position of the dissociation constant, the equilibrium. So equilibrium for a strong acid lies way on the right side. It's going to like want to be dissociated. And the weaker the acid is, the more the equilibrium position lies to the left. For the H plus concentration, if you have a strong acid, this one's actually really important. For a strong acid, your hydronium ion concentration is going to be basically equal to the acid concentration. So if I said, what is the pH of a 0.15 molar hydrochloric acid solution, the concentration of the HCl, that is the concentration of the H+. And bam, I can just take the negative log of that and I get the pH. But if you're dealing with a weak acid, the hydronium concentration is going to be much less than the actual acid concentration. I'm going to show you how to deal with that a little bit later. Also, strong acids, the conjugate base, like the stronger the acid, the weaker the conjugate base, and we can compare that to water. So on a strong acid, its conjugate base is a weaker base than water. Right? If you have a weak acid, its conjugate base is going to be a stronger base than water. All right, let's keep on going. And you're going to see, hey, wait a minute, this looks exactly like the slide we saw before, only the word acid has been replaced with base. And yes, it's absolutely the same slide, just switched around. So the stronger the base, the more the ionization equilibrium lies to the right. The strong base is going to yield a weak conjugate acid. Right? The weaker your base is, the more the ionization equilibrium lies to the left. And the weaker the base, the stronger its conjugate acid. Oh my goodness, there's something called Kb. All right, this is KEQ for a base. All right, so I'm going to write Kb again. Sorry. All right, so this really is just a KEQ. All right, products over reactants, the coefficients become exponents. Solids and liquids don't go in, so you're not going in. This is going to be boonk. H plus. All right, so this is my conjugate acid. So once the base accepts its proton, it becomes conjugate acid. Hydroxide. Boom, boom, boom. And this is all over the original base concentration. Better be in there. B. All right, kind of all that same stuff applies, right? So the larger Kb is, the stronger that base is. Right? The smaller Kb is, the weaker the base is. So the stronger the base, the more hydroxide it's going to produce. Right? The weaker base, the less hydroxide it produces. So we got that stuff. And really one more slide here. Bunch of stuff on it, but only one more slide. All right, polyprotic acids. I just want to spend one slide kind of telling you about polyprotic acids. So what do you think polyprotic means? It means many protons. So something like H2SO4 or H3PO4, like phosphoric acid, right? Those are polyprotic. They are acids that can cough up more than one proton. All right, when they do, they always dissociate stepwise. They don't just go bleh and just completely fall apart, right? The first proton comes off, then the second one, then the third one. And think about it before I actually click on this thing. Do you think they all come off equally with the same amount of ease? Like, are they willing to give up all those protons equally? I'm going to say no, they're not. All right. Anywho, the conjugate base of the first dissociation equilibrium becomes the acid in the second dissociation. So if I have H2SO4, right, put that in water, it's going to donate a proton. It's going to make hydronium and then HSO4 minus. But my second step, I'm going to start off with HSO4 minus plus water, and that's going to make hydronium and then SO4 minus, right? So the conjugate base of the first dissociation becomes the acid in our second step. And I can write those out in class if you need to see that one. All right, this is what I was kind of blurting out a little bit earlier. For a typical weak polyprotic acid, right, the Ka value is like the first one's going to be the biggest, and then they get smaller and smaller as you go. So it's less and less willing to cough up those protons as they come off. Even on sulfuric acid, which is a strong polyprotic acid, we only care about that first one, right? So it's only the first dissociation step that is important to the pH. The subsequent steps, they are truly negligible, even on something like H2SO4. There are some cases where this is not true, but we're not doing them in this class. So for our class, yeah, this is absolutely always true. So even on polyprotic acids, just worry about the first proton, and you are good to go. All right, that's that for that. Catch you guys in the next video.